Hello everyone, welcome to Reactify Labs. In this video, we will talk about ZooKeeper Atomic Broadcast, also known as ZAB. Okay, so ZAB stands for ZooKeeper Atomic Broadcast. So basically, if you see, ZooKeeper is also a distributed system, right? So it also needs coordination, right, among distributed nodes. So for that they use ZAB. Okay. Let me first discuss the structure that we are going to follow today. After that we will start with the example and then the technicalities of it. Okay. So first we will talk about the introduction of ZAB. Next we will move to components of ZAB. Okay. After that we will talk about ZAB phases. Okay. After that we will talk about the protocol mechanics of ZAB. Okay. Next we will see what are the advantages of ZAB, and then we will talk about the challenges associated with ZAB. Okay. So this is the structure that we are going to follow today. Now let's talk about why we need ZAB. Okay, let's see, is there some real life example that we can give so that we can relate to it, and then it would be better to understand the technicalities, and we would be in a better position to relate to the technical definitions when we talk about it. Okay, let's say you are shopping online. Okay, you are on Amazon shopping. Okay, so what you are doing is you are adding an item to your cart. Okay, let's say this is your cart. You add an item. Okay, and there are multiple servers. Okay, so there is a coordination service, right? So ZooKeeper is a coordination service. So let's say it has server S1. Okay, server S1 will handle your request of adding an item to the cart. Okay, but since it's a distributed system, it needs to be highly available, right? Otherwise there is no point, right? So it needs to convey its information to other nodes, but before it could convey its information to at least even any other server like server 2, it went down. Okay, now what happens is, if somebody else sees this server, like if somebody else sees your cart from this server does not have that information, right? So it will be inconsistent, right? From any other server it will be inconsistent, because whatever you added to your cart was not conveyed to the other servers, right? But if ZAB is there, so what happens is, again you add an item to your cart. Okay, server A, make sure this server A, like server 1, make sure that at least one other server knows about this update before confirming the item is in your cart. So ZAB will make sure that before this add an item tells you that yes, the item is added, this will tell the other server, see, the item is going to be added. Okay, then at least this one knows, so this will convey it to other ones, right? So this way, even if let's say after conveying it went down, okay, this server went down, server 1, still server 2 knows that the item was added. Also, let's say it could not convey. Okay, then if it could not convey, then it will not even add this item, it will tell the user to add the item again. Okay, so this is what ZAB does. ZAB tries to make sure that the ZooKeeper nodes are in a consistent state. Okay, ZAB makes sure that all servers handling your shopping cart, here in this case, can agree on what's in it, even if some servers fail or there is a network problem. This way your shopping experience is smooth and reliable. Okay, and you will not get surprises like, oh my god, I had just added it but now I cannot see it, right? So this will not happen. Okay, now I think this is clear why we need ZAB, right? Without ZAB we will see inconsistencies in the state. Okay, now let's talk about the introduction. So what is ZAB? ZAB is the consensus protocol consensus protocol, or you can say consensus algorithm, just like Raft. If you remember, I have made a separate video on Raft. Raft was also a consensus algorithm. So you might ask why we need ZAB also. Because this Raft is a general consensus algorithm, but this ZAB is specific to ZooKeeper. So ZooKeeper is also a distributed system. It has different nodes. So it needs some consensus among the nodes, right? Some consensus algorithm to achieve quorum, to take decisions, right? So for that, they use ZAB. Okay, that's why we are studying ZAB. Okay? Because it is specific. It is tightly coupled to ZooKeeper. It is ZooKeeper specific. Okay, it's a consensus protocol used by ZooKeeper to manage distributed coordination. To manage distributed coordination and ensure consistency. And ensure consistency across a cluster of ZooKeeper servers. Across a cluster of ZooKeeper servers. It ensures that all nodes in the distributed system see the same sequence of updates, which is crucial for maintaining consistency in systems that require coordination, such as distributed databases, configuration management systems, and leader election. Now, let's talk about the components of ZAB. Components. So, ZAB has two components primarily. One is leader and other one is follower. Okay. So the leader is responsible for managing the proposal process, ensuring all nodes agree on the order of updates. The responsibilities of leader includes proposal creation, where it generates proposals with unique identifiers. Then it broadcasts the proposals to all the followers. It waits for the acknowledgement from a majority of followers. As you remember, I talked about ensemble, where we take odd number of nodes. Let's say if we have 7 nodes, so it will wait for 4 of them for acknowledgement. Okay. If it receives 4 acknowledgements at least, or let's say n by 2 plus 1, then it commits the proposal and informs all the followers once a majority is achieved. Okay. So it has a leader ID basically. So we need an identifier to identify the leader, right? Leader ID is the unique identifier for each leader, which is used in leader elections. And there is also a proposal ID. Proposal ID. It's a unique identifier combining the leader's identity and a sequence number. Okay. Which tells that, okay, this leader gave out this proposal. Okay. Next we have followers. So followers receive and apply proposals from the leader and send acknowledgements to confirm. Responsibilities of followers include receiving proposals, which means they accept proposals from the leader. They apply updates to their local state and send an acknowledgement to the leader after applying the proposal. Okay. So what they send is acknowledgement message. Acknowledgement message, which includes proposal ID and the follower's state information. Proposal ID, why? Because to indicate that yes, this is a reply, this is an acknowledgement to this proposal. Okay. Proposal ID and followers state information. Okay. Okay, that's it. Next, let's talk about the phases of ZAB. Phases. First phase is leader election phase. Because there is a leader, we need to elect that leader, right? So leader election phase. Its purpose is to elect a new leader when the ensemble starts or when the current leader fails. Okay. Its process is like this. First, server initialization. Server initialization. Each server begins with a vote for itself. Then we have vote broadcast. Vote broadcast. Servers broadcast their votes, including their proposal ID and the candidate they support. And then majority rule. The candidate with a majority of votes, often the one with the highest proposal ID, becomes the leader. Okay. So vote messages include the highest proposal ID seen by the server and its vote. And there is something called election timeout as well, which is used to trigger a new election if no leader is elected in that assigned amount of time. Okay. So in a cluster of 5 zookeepers, for example, if server A has the most recent proposal ID and receives votes from other servers, it becomes the leader, right? Next phase is broadcast phase. Broadcast phase. Its purpose is to ensure consistent and ordered delivery of proposals to all nodes. Okay. So the process is first proposal creation. Proposal creation. The leader generates a proposal with a unique ID. Then proposal is broadcasted. Proposal broadcasting. The proposal is sent to all followers. Next is acknowledgement. Acknowledgement collection. So the leader will wait for the acknowledgement to come from all the followers, or at least the majority of followers, and then comes the commitment. So once a majority is achieved, the leader commits the proposal and notifies the followers to apply it. Okay. The proposal format includes the proposal ID, update data, and the metadata. And commit log is maintained by the leader to track proposals and their status. So, for example, a leader proposes a change to a configuration file. It sends the proposal to all followers, waits for the acknowledgements from a majority, and then commits the change. Now, let's talk about ZAB protocol mechanics. ZAB protocol mechanics. Okay. So, first one is proposal ordering and consistency. Proposal ordering and consistency. So proposals are ordered using unique IDs, combining the leader's ID and a sequence number, ensuring all nodes apply them in the same sequence. And ZAB ensures that once a proposal is committed, it is consistently applied by all nodes. Okay. So it has a proposal ID which combines the leader's epoch, the leader's number, and the sequence number, right? And each server logs proposals and their status to recover from failures. For example, let's say if proposal 1 has ID 101 and proposal 2 has ID 102, they are applied in the exact order across all nodes. First proposal 1, then proposal 2. Okay. Next, handling failures and recoveries. Handling failures and recoveries. So if the leader fails, a new leader is elected, which resumes proposal processing from the last committed state. Reconnecting followers synchronize with the leader by receiving and applying missed proposals. Okay. Recovery mechanism, what it does is it replays the proposal log to ensure consistency after a failure. For example, if a leader crashes after sending proposal 103, but before committing it, a new leader will ensure that proposal 103 is correctly processed and committed. Okay. Now let's see what are the advantages of ZAB. First is high availability. As I gave you in the example of the adding to cart, ZAB makes sure that your system is highly available and consistent also. So ZAB ensures that ZooKeeper remains available even if some servers fail, as long as a majority of servers are operational. This is crucial for distributed systems that require continuous operation. Second is strong consistency. Again, the same adding to cart example. ZAB provides strong consistency guarantees by ensuring that all nodes apply updates in the same order. This is essential for systems that require a consistent view of data across distributed nodes. Okay. Next is fault tolerance. ZAB is designed to tolerate failures in both leaders and followers, ensuring that the system can recover and continue operating without data loss or inconsistency. And scalability. So ZAB supports the addition of new nodes to the ensemble, which can be seamlessly integrated into the existing system without disrupting operations. Okay. Now let's see what are the challenges associated with ZAB. So first is latency. Because there are multiple nodes involved, there would be latency challenges, right? ZAB can introduce latency due to the need for multiple round-trip communications between the leader and the followers for each proposal. This can be a limitation in high latency networks. Okay. Next is complexity in leader elections. Complexity in leader elections. So leader election can be complex and time consuming in large clusters, particularly in scenarios with frequent network partitions or server failures. Next is resource intensive. Resource intensive. ZAB requires a majority of servers to be operational, which can be resource intensive, especially in large deployments where maintaining a majority can involve significant overhead. And it has a limited write throughput. Limited write throughput. The need for a majority acknowledgement, right? Because we need majority from at least more than half the number of nodes, right? So the need for a majority acknowledgement before committing a proposal can limit write throughput, especially in systems with high write demand. So if we have, if my system demands very high write, like the write should be very fast, and my ZooKeeper is waiting for multiple nodes to like tell me that yes, we all agree with you, then it's not right? So yeah, that's the challenge. Basically, ZAB is a very robust consensus protocol that that provides reliability and consistency of ZooKeeper, making it a crucial component in distributed systems which requires strong coordination, right? ZooKeeper is a system which basically manages the coordination of other microservices or other systems, right? Basically, ZooKeeper is a coordination service which manages coordination in other distributed systems. But it is also itself a distributed system, so something needs to maintain its consistency also, right? So ZAB is a robust consensus protocol which takes care of the reliability and consistency of ZooKeeper, making it a crucial component in distributed systems that require strong coordination. While it does offer significant advantages in terms of availability, consistency, and fault tolerance, it also comes with challenges related to latency, complexity, and resource usage. Okay, so that's what we understand from here, right? It's not applicable actually only to ZooKeeper, although ZAB is limited to ZooKeeper. But if we think about this, so it will be helpful, or it will help us in understanding other systems as well. So if this is something like, if we have to talk to multiple nodes to achieve something, it will produce high latency, low latency scenarios, right? It will make the system less responsive or response slow, right? So these kinds of things occur. So some pros comes with some cons, right? There, for every advantage there is some challenge. So we need to be aware of all such things before making a call of what to use, when to use, where to use. Okay. So yeah, this ends the video on ZAB. I hope you understood what ZAB is and how ZAB helps ZooKeeper achieve this consensus among its nodes, and how it's different from Raft. The primary difference was that Raft is for general consensus. ZooKeeper Atomic Broadcast, ZAB, is specific for this ZooKeeper, right? So yeah, nothing else is left in this. Okay, yeah. So if anybody asks you how ZooKeeper works, let's say you are giving a system design interview, and you say that for that system, let's say you are designing Instagram, you can say that for coordinating I will use ZooKeeper, and then somebody asks you, ZooKeeper is itself a distributed system, how will you manage the coordination or how does ZooKeeper manage? Not you, because you are not designing ZooKeeper system, you are designing Instagram. So how does ZooKeeper take care of the coordination? So you can talk about Zap there. And also, if somebody asks you to design a ZooKeeper system or like design a coordination service system, then again, you can talk about this, right? You can talk about ZooKeeper, you can talk about Zap, you can talk about Znodes. Okay. So yeah, that's all there was in this video. Thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.